The best way to understand better about refrigeration, air conditioning, and the cycles is by looking at the exercise. Okay, so I have four examples to share with you, so that you can practice more about how to solve problems related to the refrigeration cycles. So in example one, we have a heat pump. Remember heat pump. In a heat pump, we have to bring heat in. So what we want in heat pump is actually we want heat. So we want Q at hot temperature. So heat pump work based on the principle of we have a hot reservoir. So hot reservoir. Okay, here reservoir, and you want to bring it to the you want to bring heat from a cold reservoir. So this is a cold reservoir, and this is the heat pump. And to be able to bring it, so this is a Q cold and this is the QH. We need to give work. Yeah, we need to give some of work. And then in a heat pump, the coefficient of performance, which is the COP, is equal to what we want is heat KH divided by the work we provided. Heat pump is used to heat a factory during winter with average outside temperature of 0 degrees Celsius. So you want to bring in from the cold, so this is a 0 degrees Celsius, and the temperature of the factory to be maintained at 20 degrees Celsius. So this is at 20 degrees Celsius. The building heating load is estimated to be 100 kilowatt. So heating load is QH. So QH, this one equal to 100 kilowatt. Determine the minimum power requirement. So what is the W required to drive the heat pump unit for this application? So minimum power, okay, minimum power. So W min is when you have COP max, right? So okay, we achieve the COP maximum to get the work minimum. So in this case, then if you remember the equation for the heat pump, okay, so COP max is actually 1 divided by the efficiency. So 1 divided by the COP. So remember the COP then equal to QH over H, then the COP max then equal to QH max divided by QH divided by W minimum, and this one is basically 1 over the efficiency of Carnot engine, and this one 1 over this one is equal to 1 divided by efficiency of Carnot engine is 1 minus TL divided by TH. Okay, so in this case we are given the TL, it is in converted to Kelvin, so it's a 0 degrees Celsius. This is equal to 0 plus 273 equal to 273 Kelvin, and 20 degrees Celsius, that one equal then to 20 plus 273 Kelvin equal to 293 Kelvin. Yeah, so that's we get the COP max, and then you see this equation COP max equal to the QH is divided the W minimum. So rearrange, we'll find that the minimum work required is 6 kilowatt. Okay, you look 6 kilowatt, you'll be able to achieve 100 kilowatt of heat. So instead of using work as heat fully, so instead of using, for example, electric heater, we better use the electric heater to operate the heat pump to get more heat into the room. So this is example number 1. So let's go to example number 2. So a refrigerator use R12. R12 is the refrigerant, okay, as working fluid. So the refrigerant enters the compressor. So the point when the refrigerant enter the compressor, we agree that is a point 1. So it is point 1. We have a condition of saturated vapor at 2 bar, and leaving the condenser. Okay, leaving the condenser. So leaving the condenser supposed to be, this is 0.3. Okay, as saturated liquid at 8 bar. Okay, assume the compression process is 100% isentropic, and there is no superheating, no subcooling. No superheating mean point at 0.1. So what does this mean? No superheating meaning that at 0.1 the condition is saturated vapor, and then no subcooling. This one means that at 0.3 the condition is saturated liquid. Okay, so using the chart, okay, find out the work of the compression, which is this is W. Refrigeration effect is RE. So this is okay. This is our refrigeration effect. This one, okay, RE, and then the COP, and compare the COP with the Carnot performance. Carnot performance is the COP max. So the most important thing is be able to translate the given information to the chart. So I already made the solution here. Point 1, 2 bar. This 2 bar is given, okay, given in the problem. Why we know it's saturated liquid? Because it says that there is no superheating. So if you look into here, so first the first is to find out the P pressure enthalpy diagram. Make sure you bring the correct unit. So this one is the SI unit. Okay, it's bar. So it's a 2 bar. So 0.2. So it's supposed to be this value. So here's the condition, and it's a saturated vapor. So what we know is this is probably saturated liquid, and at the end of this line is saturated vapor. So this is 0.1. Okay, saturated vapor and 2 bar. So 0.1, I write here saturated vapor at 2 bar. 0.2 is isentropic compression. Isentropic will follow this line. It will follow this line. Okay, and then what we know is 0.2 is saturated liquid at 8 bar. So P2 always equal to, so this is a 0.2. So I'll write it here. So what we know is at P2 typically similar to at P3. Okay, because the condensation happen at a constant pressure. So I'll write here this is a condensation. Okay, so you bring it at 8 bar. So we stop at 8 bar here. Okay, and then the condition here is actually superheated vapor. Okay, superheated vapor, and we go to 0.3, 8 bar. Okay, and this is 0.3. What we know at 0.3 is P3 equal to 8 bar and there is no soap cooling, so this must be saturated liquid. Okay, you get that? Then we have expansion. So its enthalpy expansion is go straight away down. It's bring us to 0.4. Yeah. So 0.4 here. What we know is the pressure is equal to P1. So P4 equal to P1. And you look, the point is somewhere in the middle. So it is a mix of liquid and vapor. And then if you want to know exactly how many percentage of liquid or how many percentage of vapor, you can trace back this line down. Okay, and you find out here, yeah, this is 0.2 and this is 0.3. So it is 25% of vapor. Okay, that's the condition. So next, we look into the data and we find out the enthalpy at each point, starting from H1. So H1 is then this is the point, then this is H1. Okay, then this is H2. So H1 I already checked here, more or less 348. H2 is 374. Okay, H3 is somewhere here, equal to H4. So it's really in the middle of between 220 and 240. So this is H3 equal to H4 equal to 230. Okay, next we need the temperature. TH and T low. So how we can look into TH and T low. I'll highlight the value so it's not really blurred. So you see the temperature is given in this number. So this, for example, highlighter. So for example, this is minus 50, you see it, minus 40, minus 30, minus 20. And then TH is somewhere here. This is 50, this is 40, this is 30. So it's about 30. If you bring it to Kelvin, it's 30 plus 273, which is, and then this is a TH, then you can write it TH. Here we got a TH equal to 30 degrees Celsius equal to 303 Kelvin, and then T low is here. So you got to bring T low is somewhere there. So it's in between minus 10 and minus 20. Okay, and then I write it here minus. So it's corresponding to a moment. It's around, I think it's minus 11 somewhere here. So it's a T, it's here. So it is, this is minus 10 and this is minus 20. So it's a minus 11. You get a T L equal to minus 11 degrees Celsius, TL equal to 262 Kelvin. I already put it here. So next we look into the question, the work of compression is compression is between 0.1 and 0.2, so it must be H2 minus H1. So here H2 minus H1 is 374 minus 348 equal to 26 kilojoule per kilogram. So this is the value. Next is refrigeration effect. Remember, refrigeration effect is when actually we absorb heat in this case. So it is from 0.4 to 0.1. So then it is equal to H1 minus H4. H1 is 348. H4 is 230. So 348 minus 230 equal to 118. So next is coefficient of performance. Coefficient of performance is QL divided by work. QL divided by work. We know QL is actually the refrigeration effect. It is this one is equal to 118 divided by the work. The work is 26. Okay, you get 4.58. And lastly, the Carnot performance. We need to find out Carnot performance. We need to get the EFM is 1 minus TH over TH equal to this. This is the Carnot performance. So the coefficient of performance, then we use this equation. To get 6.41. So what does this mean? The real performance here is 4. So this the real the coefficient of performance of refrigeration is 4.5. For the maximum, okay, if we have the ideal engine in this refrigeration, will give us the coefficient of performance equals 6.41. Okay. So let's move on to the next example. This is example number 3. Due to the environmental issue related to the use of R12, it is replaced with a more environmentally benign R134A. The refrigerant, okay, enters the compressor at saturated vapor at 2 bar, so it's basically the same as the one before. Leave the condenser as saturated liquid at 8 bar. Okay, so example 2 and 3, they are identical. The only difference is we change the refrigerants. So what relevant here is that we need to change the pH diagram. We have done here. So we always start at 0.1. Okay, 0.1, from the previous discussion, we know that it is saturated liquid at 2 bar, which is correct here, 2 bar. 0.2 is isentropic, so it goes up, follow the line until we reach the pressure of 8 bar. So this is a 0.2. Okay, 0.3 is next. 0.3 is saturated liquid because there is no subcooling there. And then to reach 0.4, it follows the isentropic expansion, and then we give us 0.4. Okay, so what next? So it's very similar. If you are asked to give the condition, we know that at 0.1 we have, I'll just write it here, at 0.1 we have saturated vapor 2 bar. 0.2 you have superheated vapor at 8 bar. If you are asked the temperature, then it's very easy. You can just check the temperature line of that. So this, for example, this one is around 40. So this one, to check the temperature, is very simple. You go up, you find the temperature line here. So this is the temperature line of 40. See, this is 40. Goes here, this is 40. So P2 then equal to 8 bar, T2 equal to 40 degree Celsius, and yeah, it's a superheated vapor. So similar to the previous step, from the chart we can find the enthalpy value at each point. This is the H1, then this point is H2, and this point is H3 equal to H4. Okay, we summarize it. Then we can calculate the work of compression. Compression is 0.1 to 2. So this is compression. And this one is condensation, if you want to write. This is evaporation. And this step is expansion. Okay, so we get value H1 295 kilojoule per kilogram, H2 is 325 kilojoule per kilogram, H3 equal to H4 equal to 145 kilojoule per kilogram here, 145 kilogram. This one is 2. Yeah, I know this is a lot of estimation, but kilogram, and H2 here equal to 325 kilojoule per kilogram. Okay, so the work of compression easy. It is H2 minus H1 equal to 30 kilojoule per kilogram. The refrigeration effect H1 minus H4, which is 295 minus 145 equal to 150 kilojoule per kilogram. Coefficient of performance, that one equal to QL divided by W, or refrigeration effect divided by the work of compression. This is equal then 150 divided by 30, then you get 5 for that. Carnot performance, you need to find out the temperature. The temperature here, okay, it's minus 30. Okay, this is minus 30 degrees Celsius. This is TL, and TH is somewhere here. TH is somewhere here. So if you look, that will be more or less the same as the one before. You can see this is minus 40. Okay, you get 263 Kelvin. So this is TH. So there is minus 30, and this is around. So you see, this is 40. Okay, this is around 30. So it's TH equal to 33 degrees Celsius or 3.3 Kelvin. So then we find out the efficiency of maximum Carnot efficiency is 0.135, and we'll be able to calculate the COPM. You look, irrespective of refrigeration, if the temperature high, TH and TL is the same, it will give you the same performance. What obvious from this example compared to the previous example is we have a higher COP here. Here we get a COP of 5, and previously we get COP of 4.54. What does that mean? So I manage, so when I have a higher COP in refrigeration, it means that I can, with the same amount of work, I can send out more amount of heat. That is basically what it says. Because when you have a COP equal to 5, means that for every kilowatt work I provide, I will be able to send out heat of 5 times work I bring in. That is the definition. Okay, so next we go to the last example, which is example number 4. It's a quite interesting question here. Okay, a refrigerator employing R22 refrigerant, which is difluoromonochloromethane, operates under sub-optimum condition. Due to inefficient evaporation, okay, the refrigerant enters the compressor with 90% of vapor at pressure of 1 bar. Look, it's 90% of vapor at 1 bar. Normal refrigerator, and when the refrigerant enter the compressor, normally it's saturated vapor. Saturated vapor means 100% vapor. Okay, at the corresponding boiling point of the refrigerant condition. But in this case, because of inefficiency, it's not 100%, it's just 90% vapor. Okay, the compressor work normal. Okay, it's increased the pressure to 10 bar isentropically. And then also here, the condenser is also sub-optimum, which condense only 80% of the vapor. So normally, okay, the optimum refrigeration, we try to get it saturated liquid, but here in this case it's only reach 80%. So it condense only 80% of vapor, means we can only produce 80% of the liquid instead of 100% liquid. Okay, and then the question is, by using the pH chart of R22, of course R22, estimate the coefficient of performance of the current condition. Compare the current COP with the optimum COP, so we call it COP optimum here, and the COP ideal, which is the Carnot performance. Okay, the same as before. The step is we need to find out appropriate pH chart for R22. So we have it here, and then we need to address point by point. So to make it easier, instead of starting with the sub-optimum condition, I start with the optimum condition first. Okay, so in the optimum condition, we know that point 1 here, point one, okay, that is point 1. It is saturated liquid, saturated vapor at 1 bar. So this is 1 bar saturated vapor, that's correct. Then it go up isentropically, so it follow this line. So it's a parallel to this line. Yeah, so we get this point. So we know at point 2, if you ask more, point 2 is P2 equal to 10 bar. The condition is, so the temperature is, you see the red line, the temperature is T equal to 60 degrees Celsius. Temperature is 60 degrees Celsius. What else there? If you ask, what's the condition here? Condition is superheated vapor. That is condition at point 2. So this is point 2. So next we go to point 3. So we have condensation. This is a condensation. In the condensation, it go to the saturated liquid. So 3.3 is saturated liquid. Okay. If you ask what is the pressure, pressure is obvious. It's given in the problem. So P. So this, sorry, 3. This P3 then equal to 10 bar. If you check the temperature, so it's a T3, temperature at point 3. This is equal to actually TH, right? Equal to, you check here, that's slightly above 20. You have a 20 line at 9. Here I write it 22. Yeah, 22 degrees Celsius. 22 degrees Celsius. It's correspond to 295 Kelvin. 295 Kelvin. Yeah, that's the thing. So we stated here 295 Kelvin. And then at point 4, so what happened at between 3 and 4? 3 and 4 is isenthalpic expansion. So this is expansion. Okay, expansion. So it's bring it down to 0.4, and then at 0.4, what we know at 0.4, we know that P4 equal to P1, so equal to 1 bar. So I will write it. So okay, so I'll write it where? I'll write it here. So it's P4 then equal to P1 equal to 1 bar. If you ask what's the condition, the condition is condition C. It's you see it's in between the saturated liquid and saturated vapor, so it must be a mix of liquid and vapor. What is the percentage of liquid? You can check. This is okay. This is 10% vapor, 20% vapor. This is about 30% vapor. So so you have liquid plus vapor with 30% vapor there. If you ask what is the temperature, this temperature is TL, is T4 equal to TL, and you can see it very clearly there. The temperature is minus 40. So it's minus 40 degrees Celsius equal to 233 Kelvin. That's basically it. Then we check the enthalpy. So we check H1. H1 is here. H1 equal to, you see it is somewhere in between 650 to 700, but it's close to 700. So I will write it here as 690. Yeah. Then H2 is pretty close to 750. Yeah, but it's not 750, so I just guess it's around 745 kilojoule per kilogram. And then we have H3 equal to H4 here, in between 500 and 550. So here are just very close to the middle, so it's 525 kilojoule per Kelvin. That's it. And then we address like the normal, what is the work of compression. This is the compression work, that's equal to H2 minus H1. Okay, so H745 minus 690 equal to 55 kilojoule. We have that. Refrigeration effect is the one where we take when we absorb heat. So that is during evaporation. This is evaporation. So this equal to H1 minus H4. In this case, equal to 165 kilojoule per kilogram. So next we can find out the coefficient of performance of optimum refrigeration, which then equal to QL divided by work. QL is the refrigeration effect, 165 divided by 55, which is the work. Then we get it is equal to 3. And then the Carnot performance, we have defined the TL and TH. And here we obtain that actually if you, okay, the Carnot performance is 3.76. So our optimum performance is 3, ideal performance is 3.76. Next question is, what is the current performance? You know that if you go back to the problem, we have a sub-optimum operating refrigeration. Okay. So when we analyze the sub-optimum condition, it is exactly the same. It's not exactly the same. We have to define each point. So now remember the information is we have 90% of vapor at 1 bar. So we have pressure at 1 bar here. Instead of being here at saturated liquid, it is a little bit on the left. And we look, this is 100%. Okay, this is the line of 100% vapor, and this is the line of 90%. You can see it from this is 0.9. So the point is here. Yeah, the point is that is 0.1. So I'll see this is 0.1. Okay, it goes up to 8 bar, and okay, you follow the isentropic line, the blue line. We follow this line. Okay, in this case somewhere here, and this is the point 2 in this case. You can see point 2. If you ask me what is the P2 equal to 10 bar, it's given in the problem. Okay, the condition of the point 2 is probably close to saturated, so I would say it is superheated, so slightly superheated vapor. Okay, and you see what's the temperature. The temperature T2 equal to, you see there, it's in between 20 and 80. Yeah, most probably 25 or something. Yeah, 25 degrees Celsius. Okay, so then it goes to the condensation. Normally, if we do optimum condensation, it will go to this point. Yeah, so this is the optimum. So this is a 0.3 optimum. But we have a sub-optimum. It's only condensed 80%. So 80%, 20% liquid. This is the line of 10% liquid. So this is the line of 20% liquid. So we have around here. So this is 0.3. So if you ask the detail of 0.3, you have a P3 equal to 10 bar. We have what else? The condition of 3. So its condition of 3 is we have it's given in the problem 20% of liquid, and the T3 you can see there it's around 20 degrees Celsius. Yeah, 20 degrees Celsius. Okay, and then we have expansion to 0.4. So this is 0.4. This is expansion. I'll write this is condensation. Okay, and then what is condition at 0.4? At 0.4, I will write some here. Okay, I'll write here. It's we have a P4 equal to 1 bar. Okay, T4 equal to TL. The same as before, is around minus 40 degrees Celsius, equal to 233 Kelvin. That is T4. What is the condition of 4? We have, you can check this one. If you trace down this line, okay, it goes to this point. So it's 50% of liquid plus 50% of vapor. That's the condition. And next we go to the enthalpy value. So you see that this is the H1 equal to around 660, I think 660 kilojoule per kilogram. And this is point is H2. If you see it from the chart, slightly more than 700. So I will 710 kilojoule per kilogram. We then go to H3 equal to H4 at this point, somewhere in between. So it's around, I think 570 kilojoule per kilogram, and then we do normal. So what is the work of compression? It is H1 minus H2, we get 50. Refrigeration effect, you notice that we, in this process, the compression work is exactly the same as the one before. It's what is underperforming means. Underperforming means the refrigeration effects is much lower. So refrigeration effect we obtain during the step 4 to 1 during the evaporation. And here we have a QL. Okay, and our QL now is slightly low. So when we check the coefficient of performance, okay, that will be QL divided by work. It's much less than what we obtain in the optimum operation. That is all. So I can make summary. The key concept to understand the refrigeration and the cycle is, first we understand how to use the pH table, pressure enthalpy table. We know the condition of the fluid when it is subcooled, when it's saturated liquid, mixture in between liquid and vapor. We have also condition at saturated vapor, then superheated vapor. We have a critical condition. Above critical condition, we have supercritical liquid, right? So that's the thing. Then we need to be able to translate what does it mean, the condition given in the problem, translated into the P-chart diagram, form the diagram, and do the normal analysis. It's quite simple. Okay, finally, the only way you can really understand, because there are a lot of steps here, the only way you can really know if you understand well is to work on the example. Okay, try to redo this example compared to the discussion I provide here. And lastly, you can go to the assignment problems and work on it. You're welcome if you have any question for this one. That is all for tutorial of topic number 6.